0.1 liter.
Why does milk look like a
he's gonna start.
Oh, because we're recording.
Oh.
Come on, man.
What do you have for pH?
It's 12.3.
That's wrong.
Yep. Well, no, what did I do wrong? I did something wrong.
That's what I did.
The hydroxide concentration is 0.02. Oh, 0.02. Yeah. Okay. I was thinking it would give us an exact pH, but it's 12. Say it again. 12.4. 12.3. Around there.
Oh, sort of like a human drop.
Kind of.
That's what I said.
Oh, sorry.
Eric's getting heated, guys.
Eric, I'm really sorry.
No, it's not okay.
Will you look over here? This is the titration curve when you're titrating a weak acid with a strong base. One thing I want to make very clear on here. This region right in here, from there to there, we had a sharp increase at the beginning, but then it leveled off. Why did the pH not change very much in that middle region here around the halfway point? Oh, it all got neutralized there. Why was it flatter here? Because it was a buffer. Yes. In here, there was some acid and some of its conjugate base preventing the pH from changing very much. At the beginning, it was not a buffer, so we had a sharp increase. But then you got this buffering action going on. Resist change in pH, right? That's good to know. I have a picture on the next page of a titration of a different weak acid, not HOCl this time, but it's acetic
It's
acid.
like unzipped.
I have a question for you.
I have an answer.
Nice. Would you be able to look at this graph and determine the Ka of acetic acid?
What?
Yes. But it
Seems
was
like a lot of steps to me.
The answer is I cannot determine it.
But it is.
Someone probably could.
Someone probably could, but not me.
Oh, you just have to take the
Okay. Mr. JD has a proposal for us.
The halfway point.
Oh, JD. Tell me again. Even so Rithi can understand. Yes. We learned that thing about the halfway point. Was that making kind of a big deal about the halfway point?
Yeah.
Where the pH is equal to the pKa. Now, can you tell where the equivalence point is? It's right there. Right. In fact, it's marked. Okay? The equivalence point is right there, the sharp increase. So it took 25 ml of the sodium hydroxide to get to the equivalence point. Half of that would have been where half of the acid was neutralized, 12.5, right in there. So if you go to 12.5 and find what the pH was, that's the pKa of the acid.
Wait, what?
Wait.
What?
10 to the power of
I'll say it again. At the halfway point, the pH is equal to the pKa of the acid.
So 1 times.
So if you know where the equivalence point is, the halfway point is halfway to the equivalence point, which would be 12.5 ml. So if you know what the pH was at the halfway point, which is right around 5, 4 point something, that's the pKa of the acid. And you can identify with K of the acid. Farouk? Now this one does not have a sharp of an increase. You would take about the half, look at what that volume is and what that volume is, and then just go halfway. Now your lab data will be similar to this. It won't be as distinct as that. It's going to be more like this. So you just want to have what is the approximate midpoint of this? That would be the equivalent. Then if you need the halfway point, cut that in half and then read the pH. Okay? Nice. All right. We're not done yet. We got 15 minutes. That's plenty of time. We can.
That's like 5 more points right there.
Nothing. Oh, I was saying, can you look at this and determine what the Ka of acetic acid is? Yep. So you can know the pKa from the halfway point, and then just 10 to that power is the Ka. The next thing that we're going to do is, and we have to get through this before we can do the lab. And it's going to be all the exact same thing. We're going to take a weak base and titrate that with a strong acid. This was weak acid being titrated with a strong base. So, it's going to turn out to be all the same thing, but opposite. It's the same but opposite.
So we can just like reverse the graph a little bit.
So we're starting with a base. It's not going to have a low pH. It'll have a high pH. Then we're going to add acid to it. That's going to bring it down rather than going up.
So,
Do you expect to have a buffering region and a sharp change at the equivalence? All that's going to be the same.
how about we just like put a mirror
So
over
now
there?
that we
and
talked
then-
about it,
I think we probably should.
Oh,
Think so? All right, so we're going to deal with an organic base known as pyridine. Pyridine is, it's got this formula. If we can go back to the organic chapter, can we do that for a moment?
no. It's an
No.
amine. It's an amine compound.
Oh, it's an amine compound.
It is an amine.
Two, I'm so smart.
Even more than that, though. Check this out. No.
I didn't know. No. I didn't
Oh,
know.
yeah.
I thought fuel was the points.
It's a benzene ring,
I was like, what?
but one of the members of the benzene ring is not carbon, it's nitrogen. So each carbon that's there still has the H attached to it, and then that lone pair on the end is a place that would attract a hydrogen. Yeah, so this is not benzene. But it would be a benzene ring.
Why are we using
I'm out of
like
shit,
complex compound?
But it is still an aromatic. You would consider this to be an aromatic compound. There's resonance that happens.
Exactly.
What is
So
that?
why use this?
It's a base. So that's our, now is it a strong base? No, it's pretty wimpy. 10 to the negative 9th kb.
I'm stronger.
That's like all right.
I don't know what I'm talking about.
We want to, the first data point is where no hydrochloric acid has been added to it. So we're just going to do a straight up ice table where pyridine C5H5N is added to water. Well, you can't complain about this. Don't. You got to stay positive, remember? Now, what's the conjugate acid of C5H5N?
C5H5 and H plus.
You got it. C5H5 and H plus.
Oh.
I'm so proud of you, Eric.
Huh. Well, you guys are pretty sharp.
Oh.
All right, so there's the chemical reaction. We know the concentration of this was 0.1. This and this are 0 at the beginning, so it's going to shift to the right to the equilibrium. Can we do a little fast forward action on this thing?
Do it.
Let's do it.
The x value, when you do the ice table, x is going to equal what? The square root of Kb, which we know, times the pyridine concentration
of 0.1
initially.
Oh.
Well, yeah, we can always.
Times 0.1.
We can just use like the what was it? The thing over there because it's all 5%. Is that?
Yes, this is very weak, so you can assume 5% rule and do that. Now, do you want me to show you how I got this, or are we good?
We're good.
Good.
So the Kb is given to you. What's the now the X is going to give you hydroxide concentration. That'll allow you OH and then find pH with it. What do you get? 9.1. Give me another distinct thing. Okay. So now make sure you can get that and confirm the Gowrie is actually right. 9.12 gets us right there.
Wait, at 0 molarity?
With 0 hydrochloric acid added.
Oh,
That's what the 0 was, yeah. Because the x-axis is how much HCl. I have NaOH down here, but now I've shifted to HCl. Okay, well, shall we start adding HCl? We've got plenty of time, 10 minutes.
There.
If we can get through the first data point, then we should be ready to go for the rest of it.
Is it like going to be straight?
No, it'll be similar to the graph we just did.
if we go through all the graphs today, can we have like 100% on this?
No.
That was a dumb question. No.
That was a terrible question. Did that fix my yes?
All right. So this thing, as a base, its job is to take in hydrogens. Now we're going to add a strong acid to it. So there are all these hydrogen ions, making it very easy for the pyridine to take them out. It's weak trying to take a hydrogen off of a water molecule, but it is very happy to take one that's free. So we have the stoichiometry step. C5H5N plus hydrogen ion yields with a single direction arrow. Remember this thing, and when you add a strong acid or base, it is going to be a single direction reaction. So again, we get the conjugate acid, C5H5NH plus.
Wait, hydrogen by itself is a strong acid.
Oh yeah. Well, the strong acid provided the hydrogen ion. HCl. HCl was our titrate in this case. All right, so now our number of moles, I just kept it the same concentrations and volumes. So we got 0.004 moles here, 0.001 moles here. And that starts at 0. Limiting reagent is hydrogen, so that goes to 0. This goes down to 0.003. That goes up to 0.001.
Proper equation.
Right. Yeah.
How does this come from the
How do what?
How does this come from that?
When you add a strong acid to a weak base, it's a single direction reaction. It goes to completion. So in that case, we use the stoichiometry. You've got to use the limiting reagent to find how much of everything is left
So
over.
you don't have to use the bottom.
You don't have to because we have a buffer. We have a weak base and its conjugate acid. That's a buffer. So we can use the buffer equation instead of doing this. You could do this and you get the same answer. If you like ice tables for whatever reason, you don't like using the buffer equation, stick to this. I like the buffer equation. It's fast. Yeah.
Why can't you use what was it called? The X equation.
The what?
The X equation. The X is equal to roots KA times.
Here in this problem?
Yeah.
Because that root, square root, a shortcut is only good if you don't have any product. In this case, we have some of the product.
Oh, okay.
Now the thing about the buffer equation is this. I prefer to memorize one equation. The one in blue up there at the top, that's the one I'm going to use every time. pH equals pKa plus log of Ba. The second equation is also true. POH equals pKb plus log of A over 2.
Oh, sure.
But now I'm stuck trying to memorize, okay, which is which? I'd rather memorize one and be done with it. If you're good at memorizing and you keep stuff straight in your brain, you can know those both. And it's a little bit shorter to just know that one in the purple color, because then you have the pKb of this base.
Oh my gosh.
To use the top equation, you're going to have to know the pKa of the conjugate acid. Yeah?
What if you just learn that POH equals Bob?
Dude.
What?
Because you gotta
BAB?
use the B instead of the A, like the KB. Right,
There.
kebab! POH equals kebab.
Po. Po equals kebab.
There's only peanut butter.
You got it in your brain. You won't forget it.
Sure won't.
Nice. All right. But in my feebleness, I stick to the top buffer equation. That means I'm going to need the Ka of this thing. So that means I got to take Kw divided by the Kb value to get the Ka. No big deal to me. It's fine. Or even faster, find pKb of this and just subtract from 14. That's the pKa of the acid. That's easy enough. So anyway, calculate, what do you get? You got it, JD?
I got 5.71.
Oh, that's a sharp drop.
14.
I get 8.29 with POH.
Yep, sounds good. Yeah, you're finding the POH if you're using the KB.
This is a lot of work.
Yep. Negative log of 1.7 times 10 to the negative 9 is 8.77. So, the pH equals